in the room, some of his team in terms of those that are sitting here as research assistants, research fellows, and obviously he's got a number of colleagues and also students sitting here in the audience in person here. And I think that's a mark of how well respected he is and how well regarded. He is very generous in terms of some of his work, particularly in relation to attracting funding. I know that he's certainly brought colleagues on board and that's helped them in relation to their own development as a result of the funding opportunities that Alberto's been able to bring their way. But he's also, as I say, built up quite a portfolio of work. Now, this evening, he's only going to give you a snippet of that because I've seen his presentation. And so, Alberto is very innovative and creative. Sometimes that causes us some challenges in terms of how far he extends that innovation and creativity, but he's going to stick to the task today in terms of explaining some of the, particularly looking at health from an evolutionary perspective in relation to food and how our diet has evolved across time. But health underpins a lot of Alberto's research, whether that be in looking at how we remove harmful substances from the food chain and therefore then avoid future health issues, or also in terms of looking at much more sustainable food sources and again how they can have positive impacts on health. He's also been involved in several projects which have looked at extending the shelf life of our food products as well. So therefore again there's a sustainability angle to there because it means that some of the things are not going to waste, but looking how we can include things within our diet that wouldn't maybe traditionally have been included. So while seaweed was quite a staple in the Scottish diet quite a lot of years ago, it's less so now, and I know he's got teams working on again how we reintroduce it but in a way that remains palatable to us. He's also done things with, again, looking at alternative food sources, so insects, and you're not going to have to taste any of those samples this evening, though I do know he does have a sniff and smell test, I think, is going to be doing the rounds this evening as well, because obviously we'll look at, in terms of some of those sustainable food sources, they also have to be palatable as well to individuals, and so we do quite a lot of work around about the aesthetics of that. So I'm going to hand over to Alberto. I'm sure he will take you through a very sort of interesting talk in terms of some of the work that he's been involved in, but I say that only scratches the surface of the range of activities he has been engaged in that last 11 years. So over to you, Alberto.
Thank you, Andrea, for the introduction, of course. So. Thank you to Andrea, thank you mainly to everyone here and everyone that is online to spend 1 hour of your precious afternoon to stay here and listen to my presentation. So the title of my talk of this abstract 45 is The Good, the Bad and the Ugly. So strategies to control some bad chemical compound. I've asked to Bob to introduce me with the music, but he forgot, so that is fine. So it's okay, it's fine. I hope that I will be able to give the sense, okay, from that important movies. Okay. So, this, I don't like this. Okay. No, because, okay. There we go. So, I'm going to use okay, so, I'm going to speak about, of course, food science and what I believe about some chemistry and some chemical compound. So we're going to speak about the ugly, about the good and the bad. So my suggestion is let's start before with the ugly, okay? Also because the good and the bad were already occupied. So the ugly started the journey to the food science in 2002, and where I finished my MSc in food science and technology at the University of Naples. And after I've done my PhD in agrobiology and agrochemistry always in University of Naples, And after I've done 2 years of postdoc in Institute of Biophysics in National Council of Research of Italy in Trento, I worked for a couple of years in food industry, and that were also where I will say the lower scale of the evolution that food industries in terms of evolution in quality, in terms of capabilities, but they were very inspiring for my future work as a technologist. And after I moved back to the academia, where I've done the postdoc until 2014, that I moved here as Andrea has suggested before. One things about myself, vegetarian, and I'm vegetarian now from, I will say, 30 years, so quite life ago. And of course, in the beginning, being an Italian and vegetarian has been quite sometimes a contradiction, because every time that I've been invited at home to someone, they said, "Oh, what I'm going to cook for you tonight." And of course, it's been always a challenge, but when I was asking, okay, what have you eaten yesterday? And they said, no, I had some vegetable things. And after, what you have eaten the other day? Some other vegetables. Okay, you don't eat meat all the time. So that is something important. But of course, the chat is getting much more interesting when they are going to ask me why you are vegetarian. Of course, I believe that everyone that decide their food, their diet, for example, if someone is vegan or vegetarian, is a personal journey that lead to this conclusion. First of all, I believe that we don't need, personally, we don't need where do we live, for example. We have plenty of substances, plenty of food that we can really support a meat-free diet, and that is, from my point of view, is one of the main reasons, so I can avoid the animals. But also, I believe that in the last period, or we strive to try to be on the top of the food chain, even if in the last period we are starting to eating much more meat. I'm speaking about globally, and I'm speaking about also considering new countries that are getting much more industrialized, like African countries and some Asian countries. But this is always our perception, because if we are going to consider some example of trophic level, we are at the same level of the pigs. So we are slightly more over herbivores. Okay, we are very far away from polar bears, killer bears that are at the apex of a trophic level. So, saying this, we need to try to be considered in egocentric point of view in the food chain. We should try to be much more in eco-centric point of view. So, this can enter in the chat of sustainability, and I believe that meat is not sustainable. Also because we were not born as a natural born killer. So if we are together near a cow or a pig, we struggle to kill it with our bare hands. So we transformed ourselves in killers, but everything started to change because we need to cook meat. Generally, we need to cook most of our food. Okay, and this is important, the cooking, because since we start to cook, we became humans as we are now. The cooking has made our brain to work and start to become what we are now. If you consider, for example, the amount of neurons that are present in humans are 3 times more from our, let's say, relative primates. But if you consider also our body size is quite smaller than it. And the brain is consuming, our brain, because it's from its sides, and the neuron is consuming 20% of the energy of the food that we are getting ingested. So, do we get this energy? Of course, the answer was given from Richard Wrangham, that is an anthropologist from University of Oxford, is due to the cooked food, because the cooking of the food is going to release the energy that we need. We need to cook food in order to get the energy and to feed our brain. Otherwise, we cannot be Homo sapiens. I know that there are some other ones that are below the Homo sapiens, but this is another story. So, is it only matter of ingesting a mixture of protein, carbohydrates, and fat? Not, of course not, because when we cook food, we generate also a lot of volatile compounds. And those volatile compounds, they had a massive role in creation of our brain and our attitude towards the food, towards the memories, toward our social interaction, and that is something really important. So smell is an acquired taste that we have really developed in this time. So I want to just steal a few minutes for a little smelling exercise, where I'm going to help lovely students this one. Can have someone from the back here.
Take the lids off.
Yeah. With the lids is complex to smell. So, what is it? What you are smelling now is just a combination of one amino acid with glucose, and we have heated up. Now you can see that there is a different smell from different combination between the glucose and amino acids. Okay. I don't know if you never experienced this type of experiment before. Sorry for the attenders that are online that cannot smell this fantastic experiment. But if you come on campus, I can make again for you. Some of them are totally unexpected flavor, I guess. Someone smell of also of rotten feet. Yeah. Did you notice?
Yeah, I thought some of them smelled a bit
strange.
yeah.
So, for me, the glutamic acid with the glucose is not very strong, the first one. The other one, the smell of burnt caramel. I think the nicest one, from my point of view, is the phenyllanolene with the glucose that smell like flowers. Now, this is just a few amino acids, is a few examples. Now, try to think with all the pattern of amino acid and try to think about every food that has a different pool of amino acid that is going to react with the molecule of sugar, molecule of glucose. So try to think how could be complex the formation of aromatic compounds in our food. That is quite mesmerizing. So what happened that indeed when we cook our food, and of course with the heat, molecules, they are going to change. And inevitably, we are going to form bad and goods. Probably I'm going to speak about before the bad, but the goods, they will be, I will mention the good as well, in meanwhile we are going to speak. So the experiments that we have done, all of us, just now, has been an experiment that was discovered from Louis-Camille Maillard from, let's say, more than 100 years ago. So it means that is still relevant, this type of experiments. And what reaction that undergoes, all the reaction that undergoes this type of they were discussing about the experiment. So he published 8 papers and exactly on the similar exercise that we have done today. You have seen that some of them were brown, some of them they were less brown. So, but no one did care much until 1950 when there was Hodge and other scientists that explain much more in the detail this reaction that is called the Maillard reaction. What is it, this general scheme of Maillard reaction? As you have seen, we have let react an amino acid with a reducing sugar, the glucose. But actually it says that every amine group with the carbonyl group, with the presence of heat, they start to react together to generate a molecule that is called Amadori compound. That is a central lab, and from this central lab they are starting to start the formation of many other molecules. For example, we have volatiles compound, for example, as the one that we have smelled now, but most important, we have a lot of brown molecules that are called melanoidins, or we have other molecules that potential carcinogenic that we will speak after, like the acrylamide and so on. So, but in general, we will say that our life without Maillard reaction probably is going to be a boring life, a total boring life. Try to think about without the coffee and the smell of the coffee, without the crisps that I think that already are finished. Okay, so crackers, chocolate, all the fantastic color of the beers and so on. So our life without Maillard reaction will be tremendously boring. So what is it, the role of the Maillard reaction in food is going to generate a massive amount of chemical molecules. Now, between those chemical molecules, some are bad, some are not nice. So during this talk, we are going to focus on some not nice molecules. For example, advanced glycation end products that are molecules that are formed with of an amino acid and a sugar as always. But what is going to happen that these molecules are also associated with a lot of non-communicable disease, and they are found in the human bodies. Also because these reactions happen also inside our bodies. So not only in the food. For example, try to think a person that has diabetes and has a higher level of sugars. These sugars start to react with the protein of the body. We have this reaction that happens inside the bodies. So, but try to think also that when we have one of compound, for example, the carboxymethyl lysine, we have the sugars that is react with the lysine, and we have less available lysine that is an essential amino acid in our food. So is detrimental for the quality of the food as well. So we need to try to understand in which way we can try to control this type of reaction, or we can form some other compound that are less wanted. So in general, when we process food for a certain reason, for example, because we need to have some chemical changes in order to improve some taste and aroma, but sometimes we're going to form some things that is called processing contaminants. And some of these processing contaminants, they require further attention because some of them could be harmful for human health. So let's introduce one of the bads, or few of the bad. This is another reaction. I'm not going to ask you the reaction after this talk, so I'm not going to, don't have to learn, of course, but as I said, we have the glucose and we have the amino acid. They are going to form again the Amadori compound, the molecules that I said before, but they are going to form also some intermediate of reaction. Those intermediate of reaction, they are called reactive carbonyl species. Those reactive carbonyl species are molecules that are very reactive, as the word says, and they can react with the DNA, with the proteins, and they are auto-feed the reaction. So it means the reaction, the Maillard reaction, starts to produce molecules that to speed up its own reaction. And those they can react again with amino acids to generate more Maillard reaction products. So it could be volatiles, could be brown molecules, and can generate also acrylamide. So remember some reactive carbonyl species, because we are going to speak about some reactive carbonyl species at the end of our talk, and some things that could be also interesting. Acrylamide, one of the pathway is that some reactive carbonyl species, they react with the asparagine. There was no asparagine today, and generate acrylamide. Acrylamide is, for now, is a potential carcinogenic compound. The IARC is deciding to make it carcinogenic compound, not potential. It's genotoxic and neurotoxic, and we have exposure. It's been found in food in 2002. It's been found, it's been discovered, but it was already present, of course. And there are many foods that we eat every day. For example, French fries, crisps, cereal, coffee, crackers. So it's actually quite difficult to try acrylamide-free food, unless we are just going to eat boiled food, and it's going to be a boring life. You know, so so that is clear. So in 2018, the European Commission introduced finally a benchmark level where some food industries, they need to start to use that level as a guidance. So it means if a food industry is starting to have a level of acrylamide that is above this benchmark level, they need to start to produce, and they need to start make to some operation in order to try to go lower to this benchmark level. This is not yet a legal limit. So it means if, for example, if we have the benchmark level of 750 for the crisps, if a company has 1,000 or 2,000, they can still sell. Maybe the buyer can decide to not buy them, but they can still sell. Soon, we will have a legal limit, and the company, they cannot sell them anymore. And this, of course, can create a little problem. Of course, with colleagues around the world, since there was the discovery of acrylamide, of other Maillard reaction and products, there are needed some mitigation strategies to try to reduce the extent of formation of this type of compound, to try to guide the reaction to form desired compounds, and to limit as much as possible the formation of not desirable compound. For example, we can play with the thermal loads. So we can reduce the temperature and the time, for example, but it's not possible all the time, because in that case we can affect the safety of the product, because we are not sterilizing the product. Or we can change a little bit the process, for example, radio frequency and so on, or under vacuum. We can use enzymes, or we can play with reactant. Reactants means the molecules that play an active role in the formation of this reaction. Or we can add external molecule to try to stop the formation of this reaction, like polyphenols, antioxidant, or metal ions, and so on. In the last few years, we have focused a lot on the work on the crisps, because crisps are, we'd say, one of the staple food of the British, and and we really have covered the work from the growing of the potato, from the harvested of the potatoes. So we have tried a different type of cultivation technique, actually even using LED light for vertical farming, to the storage of the tubers, because we have a potato season, and after the potato they are all over the year in order to be produced all the year around. After, when the potato they enter in the factory, we have started to work on the pre-processing, like blanching. Blanching is an important step that helps to remove some molecules that are precursors of the acrylamide. We have played with the blanching, we have changed the slice thickness, adding some metal ion, or adding some other additives. We have changed the processing of the blanching, for example, adding some ultrasound. And after, we have played also to controlling better of the frying, for example, adding some antioxidant, or improving the fryer controls, for example. And at the end, even in the detection of the acrylamide, because one of the problems, especially that the food industry they are going to face, the analysis of the acrylamide has been done in a laboratory that is accredited, or in our laboratory, but it's going to take at least 10 days, Francesca, for the analysis. Okay, so if you analyze, if a company is producing the crisps, and after 10 days you say, oh, wait, because your level of acrylamide is very high, what are you going to do with them? So we need to generate some solution in order that we are able to analyze the acrylamide online. So it means that the company will be able to address some processing operation at that moment to reduce the formation of the acrylamide. So what we have done, we have worked with the KP. Probably you have seen this brand, you know already this brand. and we have worked with the using of additives and ultrasounds. With additives, we have added calcium chloride and citric acid. Citric acid is a molecule that you know that is present in citrus fruits. We tried before, of course we have optimized, we tried before some concentration, but were not very appealing as a taste. We have reduced the concentration, but we managed to having a nice reduction of the acrylamide. Of course, working on the literature, we didn't done anything that is of a great novelties, because if we search on Google Scholar, for example, where you are searching acrylamide reduction, there are thousands and thousands and thousands of papers on the acrylamide reduction, but most of them, I will say 99.9% of them, they've done in a lab scale. The application in the food industry is a different story, is a total different ball game. Because in the lab, we have a fantastic controlled environment, all the crisps, they have the same size, we can play as we want, we can have a reaction timing of half an hour, even more. In the food industry, we need to be very fast and quick. For example, when we have played with the ultrasound, there are colleagues that they have used ultrasound in a lab scale where they have treated the potatoes before to be fried for half an hour. This is impossible to do this in the food manufacture. So we have used the same time of the factory, that is their blanching time of 2 minutes. We have used the ultrasound, and we managed to see a decent reduction of the acrylamide. Why the ultrasound was performing was good? Because it was helping to removal of some glucose, some reducing sugar that were reacting in order to form the acrylamide. While another work that we have done, that we are actually doing with Taylor's, that is just a company that is a few miles towards Perth. We have used again calcium chloride, and we can see that there is a massive reduction of the acrylamide content. And we are working also to adding some polyphenols. So we are using some good compound in order to fight. And we can see that there is a fantastic reduction of the acrylamide. Of course, this work, especially with the Taylors, has generated already a 10 millions of a further income for this company, because they have managed to access to new contract with the KTP that we are working together. So it is quite an important piece of work that we are doing together. But is it only the acrylamide, the bad one? No, of course the answer is no. Now, for example, there are non-desired volatiles. Before Andrea was spotting one of the provettes that we were smelling before was not very nice. Now, try to understand that if you are going to having a UHT milk, a long shelf life milk, sometimes you smell it, there is like a pungent smell that you don't want, because, for example, you want that everything should smell like the fresh milk, and in that case is a non-desired. But of course, if you are having a barbecue, you know that also Andrea, she loves the corn on the barbecue, but also the corn has a nice smell on the barbecue. That is still a nice smell, that is something that we want, and actually we can smell that from Andrea's house. She's having a barbecue even from some kilometers, you know, that is very important, you know, and the next time Andrea maybe is going to invite us for a barbecue. Okay. Yeah. So, of course, as I said before, there is the formation of advanced glycation in the product. That is something that we don't like. Okay, but there are formation of many other processing contaminants that including furans, and furans are really important, especially for baby foods, where we have some really important issues because they are toxic compounds, either heterocyclamine or compounds that are formed during the refining of the oil, like 3-monochloropropandiol and so on and so on. So that is just a little snapshot of some bad compound, but let's starting to think about some good one. We mentioned some polyphenols, especially the tocopherol that we have used for the tailors, and they work very nicely to try to fight some extent of Maillard reaction. But with this work of our student, ex-PhD student, now is not a member of staff, we have used compound generated from the Maillard reaction to autofight the reaction itself, and in particular the melanoidins, the brown molecules. So you have seen in the tubes that some molecules are brown, they are generating some brown molecules. But in general, what is it? One of the mechanisms that we have working with the polyphenols or on the melanoidin. This is an example of the glucose. The glucose is going to transform in a reactive carbonyl species, the molecules that are starting to feed the Maillard reaction. But when there is a polyphenols, a phenolic compound, this phenolic compound gives a fantastic hug to this compound and is starting to hold very tightly, that is going to avoid to further react. Okay, so means is removing these reactive species from the reaction mixtures and stop or hold the reaction. So in this work that was done from Slim, we generated an ingredient from the brewer's pentagrain. So we generated the melanoidins from the brewer's pentagrain, because one of my work is especially to try to recover as much as possible from food waste, always for circular economy. So we generated these melanoidins, and we have seen that this melanoidin has a fantastic trapping capacities and was able in a milk model system to make a nice reduction of formation of advanced glycation in the product, in this case the carboxymethyl lysine. But we have seen also that in the opposite way, in the milk there were much more lysine. So the lysine was more available. So it means that the thermal treatment is not so strong inside our milk. And that was a good thing. But can we translate the same approach to other contexts? Yes. We have translated the same approach to electronic cigarettes. So total a different world from food, we think. Some years ago, a colleague from St. Andrews University called me and said, Alberto, you work in food. I was a geologist, that now I'm interested in work in the electronic cigarette to understand the toxic compounds that are generated. I think that we need to collaborate together, because I believe that there are some reactions that are food related, but he was thinking much more about the flavoring compounds. So just to give you a bit of information on the electronic cigarette. Electronic cigarettes are fantastic devices that are needed for smoking cessation. And they try to mimic combustion cigarette. Combustion cigarettes are, as you know, there is the combustion that happens on the fronts, and after the mainstream of gas is passing through the main cigarette, and after it's going to a filter. The electronic cigarette is mimicking similar things. We have an e-liquid where we have the wick that is immersed in this e-liquid. We have a battery that gives electricity to the coil. The coil is getting very, very hot and is going to generate our vapor. Okay? So, what is the composition of the e-liquids? Of course, already these pictures is nice because it's very colorful, and that is a problem because now all the kids, they're starting to vape, and this is creating little issues that we need to be aware. Because, as you can understand, these electronic cigarettes are not risk-free. Generally, in the liquids, we have glycerol, propylene glycol, so two main components, and some water that are the main carrier solvents. We have, of course, the nicotine, because nicotine is necessary, especially for people that they want to quit smoking. And they have a lot of flavorings, you know, like the one that we have strawberries, someone likes bananas, or mint, and so on, and so on, and so on. So, and of course that is creating a massive problem. And my colleague said, oh, Alberto, but there are a lot of food related, so shall we analyze some food related flavors because they could be of interest. But probably the most important things, when I started to study the reaction, I said, and the more toxic compounds that are generated in the electronic cigarette are the formaldehyde and the acetaldehyde carbonyl species, and studying the reaction of degradation of the propylene glycol, I'm going to check that after is going to oxidize in acetol, and after is going to oxidize in methyglyoxal. Methyglyoxal is exactly the same enemy that we spoke before. Is always a dicarbonyl compound, is a carbonyl species, the one that react to generate acrylamide and so on. So and I said, okay, wait a moment, can we trap it? If we are going to stop his reactivity, maybe we are going to avoid the formation of formaldehyde and the acetaldehydes. Can we use some polyphenols? Can we use exactly the same science, the same chemistry that we have used for to stop the acrylamide or stop the other Maillard reaction in the product? Of course, there are other strategies to reduce the formation of species. For example, reducing metals, because metals can help to instigate this reaction. That's why coils sometimes are made in ceramics, or reduce the temperature of the coil and so on. So what we have done, we have added inside our model system of e-liquid model system, we have added gallic acid, hydroxytyrosol of epigallocatechin gallate. So this one, the epigallocatechin gallate, is the main polyphenols of the green tea. The hydroxytyrosol is the main polyphenol of olives. And the gallic acid is a general phenolic compound that is present in all vegetables. And what we have seen to reduce 72% of formaldehyde and 100% of acetaldehyde formation. So we found and we studied also the adduct, and to confirm that our hypothesis was exactly that one. So concluding, I don't know what is it at the time, I'm not looking at the time at all. What is it, our take-home message? Is the problem only of the food industries? No, the problem is not only the food industries, because we produce this type of compound at home. Before I was having a chat with Andrea, and Andrea, she told me that her husband is one of the main contributors of acrylamide in her household, okay, because she really likes the burned toast. So, for example, when we fry potatoes, when we bake, you know, and in our cooking processing operation, we love maybe crunchy and roasted food and so on. You know, so that is so we can limit the acrylamide that is produced by the food industry, but when we go in our mom and when we have our Sunday roast, we are having the full load of the acrylamide. So it's important that actually we should start to educate ourselves, but we need to start to educate also the further generation to try to mitigate also inside the household the formation of this type of compounds. So what we can try to do in order to do this, first of all, as also the Guardian suggested in some years ago, going for gold and not going for brown. So when we are using our toast, we need to go for gold and not for totally burned toast. Or for example, when we are baking our potatoes, so when we want to fry our potatoes, it's important to adopt similar techniques that are happening in industrial. So for example, try to wash with plenty of water, or sometimes even boiling them before to baking them, in order to try to remove as much of reducing sugars that can generate acrylamide. Or for example, when we want to do the barbecue, for example, or when we want to roast our meat, for example, will be fantastic if we can make some marination with some nice spices that are full of polyphenols and antioxidants. Or for example, frying with a really good oil that is rich in polyphenols. If we don't have a good oil rich in polyphenol, we can create at home. For example, we can try to infuse our oil of rosemary, oregano, for example, and leave it over there for a little bit of time, and after we can start to fry to reduce. But of course, I don't want to try to scare you, but that does mean we don't have to eat any more of this type of compound, but we can try to put some attention. For example, of the coffee. The coffee, if we choose, for example, a very dark and roasted coffee, that has less acrylamide from the, let's say, less roasted coffee, because the acrylamide is reducing towards the roasting because it's polymerized and it's going to be destroyed while the roasting. So that's some take-home message that we can try to take from this one. So, concluding, first of all, I want to thank all my research team, from Slim, Francesca, that is present here, Ivan, that I know is probably injecting samples in the LCMS, Vishnu, that is there as well, Alma, that she's playing football, Sutasiani, that is in Italy, and Simran, that has a name that is strange, but for everyone is Simran, and Gloria, that is back in her own country. Of course, fundamentally, I need to thank my previous past research team, like Moira, that's working in Diageo, Bruna, that we started to work on the electronic cigarette together, Loic and Fazilla, that also they left the team. And this is just a tiny selection of thanks from the wider team. So from colleague from Zimbabwe, Professor Jacob George, and Ed Steven, respectively, from Dundee University and University of St. Andrews. Of course, Dario, Antonio Troise, Andrea Scaluni from Proteomic Department of National Research Council, colleague from University of Naples, from University of Granada, and so I can keep talking for good. Okay, so I think I finished. I don't know how long it was. If you have any question, I will be happy to answer.